Hello, my name is Patrick and I'm a research fellow at Macquarie University, located in Sydney, Australia. The focus of my talk will be regarding the design of artificial agents, as well as quantifying the interaction dynamics between such agents when teaming with humans. Before I begin, I want to first acknowledge both Macquarie University as well as the Australian Research Council, who have provided funding to support this research. I also want to say thank you to both Mustafa Demir and Micah Carroll, who have provided me with useful slides to help summarize their research. Their work was the inspiration for the experiment that I'll be discussing in this talk. So, this talk explores the possibility for human autonomy teaming. As opposed to artificial agents that can augment information or automate certain functionality, human autonomy teaming involves integrating artificial agents as synthetic teammates, which are self-directed in their behavior and can collaborate with humans. For human autonomy teaming to be possible, synthetic teammates must be fundamentally social. They need to be able to detect the intentions of humans that these agents are interacting with and select behaviors that contribute meaningfully to the shared goal without interference. A useful starting point to understand how artificial agents can collaborate with humans effectively is understanding kind of the dynamics which enable effective all-human teaming to be possible. And so, within the theoretical umbrella of interactive team cognition, a lot of research in the past decade or so has kind of looked at understanding the dynamics of all human teams. And so for this, team cognition or collective intelligence is best understood as an activity that unfolds over time, where the team itself is treated as a dynamical system whose behavior is emergent from the ongoing interactions of the individual team members. The process that operate at the team level can be measured via the patterns of interactions between its constituent team members. These patterns of interaction can then be used to quantify a team's resilience to challenges or ability to adapt to new task contexts. A popular tool in this area to assess the functioning of teams is via recurrence quantification analysis, or RQA, which I've shown an example below. As I'll expand upon later, RQA generates plots which can illustrate the interaction patterns between team members and teams. And statistics can be obtained from these plots, which can uncover the underlying properties of the system, such as its stability. More recent research has applied recurrence-based methods to assess the differences in interaction dynamics between all human and mixed teams in a three-person reconnaissance task. In this task, teams consisted of a pilot who operated a UAV, a navigator who planned the route that the UAV must take, and a photographer whose job was to take well-focused photos of certain assets. In their experiments, Demir and colleagues varied the composition of teams by replacing the pilot with either a human participant, an experimenter, or an artificial agent who utilized an ACT-R-based cognitive model. In this task, team members used a text-based communication system, and so what was done is that timestamps from the conversation was used as a measure of communication flow between team members. Using a time series of this timestamp information, Demir and colleagues constructed what are called joint recurrence plots to determine the patterns of interactions between the navigator, pilot, and photographer. And what was found is that participants, when teaming with the ACT-R synthetic agent, had rigid patterns of interaction compared to those in all human teams, as quantified by a statistic called percent determinism, which I'll talk more about later. The rigidity in the kind of communication between members of these synthetic teams is also associated with worse performance in responding to novel challenges in the reconnaissance task compared to teams which included an experimenter, which when teams had an experimenter kind of provided a perfect balance between rigid and flexibility in terms of how teams communicated with each other. The authors attributed these findings to the behavioral passivity of the synthetic teammate in the study, as well as its lack of teamwork skills that could allow it to anticipate the needs of teammates in a timely manner. Overall, the challenge of symbolic-based architecture such as the ACT-R model is that it lacks the flexibility needed by artificial agents to adapt to the natural variability found in human teams. An alternative is the utilization of model-free methods, which train artificial agents to develop action patterns based from experience. The most promising work in this area has been embedding artificial agents in a reinforcement learning problem. Here, agents interact directly with a training environment and learn to associate states of the environment with actions that maximize the reward function. This approach has been coined deep reinforcement learning because these agents represent the policy mappings between states and actions using a deep neural network. Agents trained using deep reinforcement learning has excelled in video game tasks such as those made from Atari and has shown great promise in defeating humans in competitive task contexts such as 1v1 games like Go or team-based tasks such as Dota 2. This is due to artificial agents being able to essentially exploit the suboptimality of human behavior. At some point, humans will choke up, and at which point artificial agents will dominate. However, there is a challenge moving away from these kind of competitive task contexts to more collaborative contexts, where artificial agents need to cope with the fact that humans are suboptimal. And so a recent approach to kind of study human AI collaboration generally is to employ kind of cooperative games, such as Overcooked, which is shown right here. And so in this teams have to coordinate under time constraints to decide which food orders the team need to fulfill, in what order, and what tasks should each team member do to kind of contribute to the task goal. One particular research group, Carroll et al., kind of took this video game and created a simplified overcooked environment in order to develop artificial agents using deep reinforcement learning that can collaborate with humans. And so when taking the traditional approach of training artificial agents, whereby the artificial agent learns to solve the task by playing with a similar artificial agent, these agents are able to complete the task very efficiently. However, when these same agents have to then collaborate with human players, the agents are incapable of detecting the intentions of humans to facilitate team coordination. And so the reason why these artificial agents are unable to work with humans effectively is that there's a disconnect between the training environment for which these agents learned and the test environment, where basically in the training environment, agents were not exposed to any sort of human data, learned to solve the task on their own, and now they're put in this environment where now they're faced with a human, which have very particular ways of going about doing a task. And so an ideal solution is to include humans in the training environment for these artificial agents. However, this is not a practical solution given the sheer amount of training steps that is needed to train these artificial agents. A compromise tested by Carroll and colleagues is to embed a human model as a proxy for real human behavior during training. This was done using imitation learning, which was used to develop a behavior policy from previous human-human data to create an agent that can then serve as the partner for artificial agents during training. The result, shown on the right, was an artificial agent that was indeed more effective in teaming with humans compared to the self-play agents that did not have experience of any human data on the left side. And so research by Carroll and colleagues has demonstrated the promises of using deep reinforcement learning to train artificial agents who can collaborate with humans. This study sought to integrate these recent advances using deep reinforcement learning within the theoretical work of interactive team cognition. Qualitative observations from Carroll et al. Stated that the human-aware agent that they trained was more adaptive to participants than the self-aware agent. This study sought to quantify these observations using joint recurrence quantification analysis to assess the interactions between human participants and each artificial agent. So, in our study, we recruited 43 participants to complete the overcooked task alongside the artificial agents. Trials lasted 2 minutes, and participants were tasked to collaborate with their partner to cook and serve as many bowls of onion soup as they can within that time. The study utilized a within-subject design whereby participants completed the task with both the self-play and human-aware agents that were previously trained from Carroll et al.'s work. And so participants interacted with both agents, and the order of which they interacted with them was counterbalanced. And so kind of the heart of this is quantifying the interaction dynamics between participants and these artificial agents in this task. And so what we did is we computed a time series of the unique states for each player. And so the possible states includes the cardinal direction of each player, its position in space, as well as the object that the agent is currently holding. So whether they're holding nothing, an onion, a bowl, or a bowl filled with soup. And so for each player, that equates to 128 possible states that a given player can inhabit. We then took the time series of these states and labeled each unique state with a number. We then constructed a two-dimensional recurrence plot which identified repetitions of these states across time. You can think of these recurrence plots as kind of a Boolean matrix, which states whether or not kind of a true or false if a state has been revisited. And so let's take the top blue example, for example. What we see is that player 1 alternates between states 1, 2, 1, 2, 1, 2, and then proceeds to states 5, 6, 5, 6, so there's some rhythmicity to it. And the red player, player 2 here, alternates between states 3, 4, 3, 4, 3, 4, and then switches over to 5, 6, 5, 6, so also kind of exhibiting the same kind of types of rhythmicity. And so when you take those two recurrence plots and you put them on top of each other, and so since it's kind of like a Boolean matrix, states that exhibit true for both player 1 and 2 will also show up true on the joint recurrence plots. And so what we can then do is compute what's called percent determinism, which is the percent of all recurrent points on this plot that fall along diagonal lines. And so in this top case, since although the player 1 and 2 were exhibiting two different kind of sequences of actions, the rhythmicities of their actions were consistent across time, and so this produced a percent determinism of 100%. And so here's just an example from the actual experiment and kind of how this looks like as well. So this is the participant, time series, recurrence plot, the artificial agent, and then the joint recurrence plot as well. And so we refer kind of the inverse of the percent determinism from these plots as interaction flexibility. So the lower the determinism, the more flexible the interactions are between team members. In addition to the quantitative measures, we also included qualitative measures to assess the interaction of participants with each artificial agent. So a composite score was created from each of these questions, which were each rated on a 5-point scale. To summarize our findings, participants, when teaming with the human-aware agent, were able to serve more bowls of onion soup than when playing with the self-play agent. This was also reflected in the qualitative measures, so participants preferred working with the human-aware agent as opposed to the self-play agent. And then also, when relating percent determinism with the bowls of onion soup served, what we find is that as interaction flexibility increases, which in this case means lower percent determinism, that correlated with an increase in the number of bowls of soup that teams served. And there was also a main effect between a human-aware and self-play agent such that the human-aware agents, when interacting with humans, resulted in greater interaction flexibility than when teaming with the self-play agents. And so to summarize our findings, our research replicated the performance findings from Carroll et al. And then further, our results quantified the qualitative findings reported by this research team by attributing differences in the artificial agents to the flexibility in interacting with human participants. Our findings also replicate the work of Demir and colleagues, who showed that increases in interaction flexibility correlated with team performance. So this study was limited to investigating just humans teaming with artificial agents. Future work will relate these findings with a new sample kind of comparing with human-human teams. And generally the benefit of using joint recurrence quantification analysis as applied here is that it can provide a real-time measure of the interaction dynamics of teams. So this opens a possibility for future work to explore whether these measures generated from these plots can be useful in steering teams to adopt preferable behaviors in real time. And then finally, future work is needed to explore alternative approaches to designing these human-aware agents. This study relied on previously collected human-human data to generate models of human behavior. In addition to this, future work can explore model-based approaches that can generate human-like behavior in the training environments of agents utilizing deep reinforcement learning. And so thank you for watching this presentation. Feel free to reach out to me by email, ResearchGate, or on Twitter if you have any questions or if you would like to discuss this research. Thank you.